Okay, let's briefly review what we learned last week. Last week we discussed the double sideband, right? Double sideband suppress carrier. So how it works is that in the transmitter, what you do is you have a carrier and you have a message, right? And you simply multiply the message with the carrier so that the message is still part of the amplitude of your carrier, right? Now, when you look at this ST into the from the frequency domain, now you see that you have passband signal in the frequency, positive frequency and also the negative frequency. So now you can see the two different M here in the frequency. So if you visualize those things, so here's a message signal that you want to transmit, and simply you multiply the cosine carrier into this MT. Now you see this kind of sinusoidal wave, which is ST, right? This is what you transmit over the air. Okay, looking at the same thing from the frequency domain, this is your frequency response of this signal. So these two are the same thing. By multiplying cosine carrier into that, now in the frequency domain, you shift it, right? This one shifted into the positive and also shifted into negative. Now you see here positive and negative passband signals, right? So this is same as this one, just time domain and frequency domain. Okay? So that's what we transmit over the air, ST and capital SF. Transmitter is simple because you simply multiply message with the carrier. However, what is happening is you need to receive it using some of the special receiver like a coherent detector. So this is a receiver called a coherent detector. And remember what this coherence means, right? What that means is you need to make the phase aligned, right? So we have a phase at the transmitter, and also in the receiver, we have also its own phase. Always we use the same carrier frequency. So carrier frequency at the transmitter, carrier frequency at the receiver, we both agreed, even before the transmission. So we already know the carrier frequency, so that's not a problem. The problem is that it always has a phase in the sinusoidal wave. And the phase at the transmitter and phase at the receiver typically does not match. And we need to make a match between the both transmitter and receiver phase in order to make a coherent detection. Okay? So coherent means phase matched, right? Phase of the transmitter, phase of the receiver, we want to make it exactly co-phased, meaning phase is zero. A phase mismatch is zero. Okay? That's what we want to try here. So receiver, in a certain sense, is not that difficult. We have ST, which is transmitted over the air. We receive it with no error. And you multiply the same carrier frequency. But in this case, we may have a little bit of different phase mismatch. If the phase mismatch is zero, then everything is perfect. Remember that what we have in the blackboard. If we have a phase mismatch is zero, then ST already have a cosine because the carrier is a cosine, right? And in the receiver, we multiply cosine again. So here at the VT, we end up having like message MT times cosine square. Right? I'm talking about when mismatch is zero. Okay? When in that case, we have a cosine square here, right? And cosine square is basically the same as DC component plus cosine 2 frequency, 2 times frequency. Okay? This is just identity, trigonometric identity. So using this identity, now cosine square can be split into DC plus some other high frequency component. And this high frequency component will be removed by this low pass filter. So eventually, when you go through the low pass filter, you end up getting only the DC component. So the DC component, which is this one, half, and we have a message right here, right? Message times cosine square, right? So the high frequency component is removed. Now what you have here is a half times message. So you can recover message back here perfectly, only when phase is zero. However, phase mismatch may not be zero because typically phase is random. So therefore, if you have a certain phase mismatch, then mathematically we can write it this way. Here Vt, you are multiplying a cosine with a certain phase mismatch. So you have St, which is incoming signal, times cosine 2 pi of Ct plus phi, this one, right? But St is the same as mt times cosine carrier. So it's like mt times cosine 2 pi of Ct times cosine 2 pi of Ct plus phi, right? So it's like a same cosine with the same frequency, but this one has a little bit of phase mismatch. So when you have two cosine multiplied in this way, now using the identity like this, cosine theta 1 times cosine theta 2 equals to this one, right? Product of two cosine now can be an addition of two different cosine. And inside of here, theta 1, theta 2 is added or subtracted. When you use this identity here, since we have a multiplication of two cosine, now using this identity, we can rewrite this one into this way. So this one is the same, basically, right? Just simply using this identity. Now you are adding these two components, like theta 1, theta 2, then you're going to get this, 4 phi fct plus phi, and use this one minus this becomes only phi. So you have a phi component. So that's why you have this. Again, this is still Vt right here. Now next thing to do is put this signal into the low pass filter. When you do that, this high frequency component is now removed. You only have this cosine phi multiplied into this part. So you can recover this one at the output here. So that's eventually our output, okay, from this coherent detector. What you can see here is that you can recover the message back here, and there's a certain coefficient, which is fine, but it is multiplied by cosine phi, and phi is random. So if you're unlucky, the phi is 90 degrees, you get 0, okay? And this value is going to be maximum when phi equal to 0, because phi equal to 0 means cosine becomes 1, so you're going to get the maximum, okay? So that's the effect, what we call as a quadrature null effect. When the phi or phase mismatch is quadrature, or say 90 degree, or phi over 2, that's 90 degree, right? When the phase mismatch is 90 degree, you're going to get null, meaning 0, right? That's the quadrature null effect. So that's really bad, right? Because we cannot control the phase mismatch. You don't know, because that's random. So if you're unlucky, you get 0. You're lucky, you get some signal. So that's very bad. So that's why what we need to design is we need to design a co-stas receiver. Okay, the previous coherent detector, this one looks pretty simple, but this is not enough. Because sometimes you will get 0, but you cannot do anything because that's random. So what we need to do is we have to design this co-stas receiver, and here is a block diagram of co-stas receiver. And the difference between the previous coherent detector and this coherent receiver is that this one is actually just two coherent detectors, just in parallel. Okay, two, same thing actually. This upper one is called the I channel. This bottom here we call as a Q channel, or in phase or quadrature phase. Okay, so we call this a two different channel, but each channel looks identical. Okay, each channel, let's say I channel looks exactly same as the previous coherent detector, and the Q channel is almost the same. The only difference is you are multiplying sine carrier, not cosine. That's the only difference. But the cosine carrier, sine carrier is almost the same, right? In order to make a cosine, in order to make a sine carrier from the cosine carrier, what you need to do is you need to make a 90-degree phase shift. So because we both are same frequency, what you need to do is you generate the cosine and then 90-degree phase shift, that becomes the sine, right? So it's very easy to make the sine. So somehow hardware point of view, this hardware is exactly the same thing. We only need additional phase shifter of 90 degree. That's it, in order to make a sine. Okay, so that's the only hardware we need. Once you make this co-stas receiver, Now, what you can see is that, let's say you have some ST incoming signal, and there is a phi, the phase mismatch. And if the phase mismatch is 0, which means ideal case, now you get a perfect output here, and you're going to get 0 at the output here. Okay, if the phase mismatch is 0. However, if the phase mismatch is say 90 degree, in the previous case, in that case you get 0 output, right? Same here, you get 0 output here, but instead you get a maximum output here at the Q channel. So depending on the phi value, phase mismatch, sometimes you get some value here, you also get some other value here. Okay, you get, since you have two different channels, you get some output from both sides, from both channels. So what you need to do is you simply divide this one divided by this. Then it's going to be tangent phi. Okay, so you get some value here, right? You get some voltage. You also get some voltage. Let's say you get some 3 volts, just an example, right? 3 volts. Here are 4 volts. Then what do you do? 3 divided by 4, that's a 0.75. And put that into the arc tangent, inverse tangent. Then you get phi. Question? Okay. So then you can get the phi. Okay. So based on that, then you can calculate the phase mismatch by just dividing this and putting it into the arc tangent. You get the phi, the mismatch back. Okay. Once you know what is the phase mismatch, now put that mismatch little by little into the voltage control oscillator. What is this one? Voltage control oscillator always has a reference voltage. Input is voltage, output is frequency. Okay? So there's always a reference voltage. There's also reference frequency output. So when you put the reference voltage, you're always getting reference voltage, reference frequency. But if you increase the voltage or decrease the voltage, now then frequency output is changed. It's faster, sometimes getting faster, sometimes slower. Okay? So by doing that, when you have a phase mismatch, now you're gonna either make a output frequency a little bit faster or a little bit slower in order to catch up. So your phase becomes 0. Okay? You want to correct it little by little. Little by little. Let's say your original signal goes like this and your phase is delayed, phase is lagging. Let's say phase is a little bit behind. In that case, you want to make it faster a little bit, right? So in order to catch up. Or maybe if your phase is a little bit ahead, right? A little bit faster, then maybe you want to make it a little bit slower frequency so that you want to slow a little bit. And then eventually it'll be matched, right? So that way, you're little by doing feedback. This is keep running. Okay, little by little you correct it. Eventually, this phase becomes 0. So that's what we do in the Costas receiver. Later, when we talk about digital modulation or digital communication block, we're going to look at the same thing again. I channel, Q channel, every communication system you use, like your cell phone or every communication you have these blocks, I channel, Q channel. Right now, this one is analog, right? Still, we are talking about analog system. But when we talk about digital system later, we will still talk about I channel, Q channel. Same thing, same structure. Only difference is this part now becomes digital. Okay? But still, the same structure is there. So once you are familiar with this Costas receiver structure, later it will be much easier. Okay? So that's the main point of the DSB, double sideband. Today, what we are going to talk about is another amplitude modulation. Okay? So far, we talked about 2 different amplitude modulation, right? Some kind of a basic DC added amplitude modulation and double sideband. And here is a double sideband in frequency domain. Right here in the frequency domain, your original message have this frequency response. This is the original message. Now multiplying just cosine carrier, that original message here in the frequency domain is now splitted like this, and the center frequency is going to be your carrier frequency, left and right, like this. But this is a double sideband because you have, looks like a mirror, right? You have the same thing here and here again. So it's like a double side. That's why we call it as double sideband. But that's what we just discussed so far, okay, last week. Today, what we're going to talk about is single sideband. Single sideband. So there are two different single sideband: upper single sideband and lower single sideband. Okay, and let's compare this picture with this. Everything is frequency domain. So this is a double sideband frequency domain, and this is, let's say, upper sideband frequency domain view. So when you compare these two, what's the difference? In single sideband, what you are trying to do is you are taking only one side. Okay? In the upper sideband, you are taking the outer ones. In this case, positive, so you are taking this one. This is negative, so you are taking this one. So outer one. Okay? You are taking outer. This and this, outer one, that's the upper sideband. Why is it upper? Because here, looking here, this side is higher frequency than this. And here, it's like a, if you think about absolute value, this is higher than this, right? Absolute value is higher. So the upper side means upper is outer one. And the lower sideband is inner one, okay, inner. Here's inner, this one and this one. That's the lower sideband. Okay. Here, as I said, we have the same thing here, right? It's a symmetric. It's a symmetric, right? And we discussed why this is symmetric last week, right? Why is it symmetric? This is symmetric because the time domain signal is real. Remember, right? Time domain signal is real, not imaginary. No imaginary component, right? That's why when you take a Fourier transform to go to the frequency domain, now you see the two different things symmetric. However, now you see that these two, okay, left and right here, or lower side or upper side, these two looks symmetric. That basically means you have the same information here and here. Same information is here and here. It's like a double sideband, right? Double sideband. So same information is on the left and also in the right. It's like a duplicate, right? That's why in single sideband, what we are trying to do is we want to take only one side. In this case, let's think about this one. This is not symmetric, right? Here it's a symmetric. Left, right is same, like a mirror, putting in the mirror here. But this is not, right? You have only right side, there's no left side. When you take a inverse Fourier transform of this to look at the time domain signal, now the time domain signal is not real, right? This case, the time domain signal is real. That's why you see the double sideband. But in this case, single sideband, so time domain signal is now a little bit strange, a little bit weird signal, right? It's not real. Okay, but anyway, that's what we are trying to do. So simple thing is, same information is on the left and right. It's like a double. So what we are trying to do is we are taking only one side, either upper side or lower side. Okay, we are taking only one. And what is the main reason we want to do SSB? DSB works fine, right? This works okay. But why do you want to talk about SSB? Huh? Why? This is the only difference. And why do you need this one? You can see the difference here, right? The only reason is you want to use smaller frequency spectrum. Okay? You want to use smaller spectrum. This one uses a double bandwidth, right? Bandwidth is double. Look at here, the bandwidth is, in this case, the DSB case, your bandwidth is 2W. However, in single sideband, your bandwidth is only W. But we transmit same information. So typically, right, if you want to transmit the same information, using smaller bandwidth is much more efficient, right? It's all about spectrum efficiency. We want to use smaller bandwidth, okay, smaller bandwidth to transmit the same information. That's only why. Okay, that's reason. So SSB is much more spectrum efficient because it uses only half of a bandwidth. Spectrum efficiency. That's the only reason. So spectrum efficiency is very good, but as I said, now the time domain signal is not real. We need to make this one. We need to make this one from the DSP. So it's a little bit complex. That's the little bit problem. Okay, complex. But efficiency is really good. So that's what we're going to discuss. Okay, let's take a look at a little bit of mathematics behind it. Once you understand all this mathematics, then you are good. Okay, then you understand everything. So let's take a look at here. We always start from double sideband. We already discussed the double sideband. So let's start from the double sideband. We know that double sideband is simply multiplication of message and carrier. And just to let's take a simple example of message. Let's say message is simply cosine. You can make any message, but just for discussion, let's say message, we are taking a simple cosine carrier like this, and then multiply into carrier. Now our carrier is AC times cosine 2 pi FCT, and multiply by message, and message is AM times cosine 2 pi FM. FM is message frequency, right? Then it's AM, here cosine 2 pi FMT. So this is a cosine carrier. This is a message, but our message is again cosine. So it's like a cosine times cosine. It's a multiplication of two cosine. When you have a cosine times cosine, okay, cosine multiplied by another cosine, based on the trigonometry identity, we already discussed that, this will be divided into two different cosine, addition of two different cosine, right? Cosine and adding these two, like a theta, cosine theta 1 times cosine theta 2. It's like a cosine theta 1 theta 2 plus and cosine theta 1 minus theta 2, something like that, right? So we can divide this one into two different cosine like this, right? The same as before. So we have two different cosine multiplication. This one is an addition of these two, and this is the subtraction of these two. And we separate that into two different cosine terms. And the first cosine term, we call this an upper sideband. And the second one is a lower sideband. Okay, we'll talk about that in more detail, maybe in the next slide. So let's look at the upper sideband first. This one first. Okay, upper sideband first. Let's take this upper sideband and write it here. This is upper sideband. Now I put the subscript as a USSB because upper sideband. Okay, upper sideband. Yeah, something like that. So USSB. So this is just upper sideband. I'm just taking this upper sideband, the red one, right? Just taking the red one. And what I'm trying to do is I'm using another identity, cosine alpha plus beta, right? That one you can rewrite as a cosine alpha cosine beta minus sine alpha sine beta, right? That's another high school trigonometric identity. So using this cosine, okay, and from this one I can rewrite as a cosine minus sine sine. Okay, just rewrite it. So these are basically the same thing. Just write it in another way. Now when you look at this, right, the second term, what you can see now here is in the first term here you see that here is AM times cosine 2 pi FMT, which is MT, original MT. So this part is original MT. Okay. So since this is original MT, now we can say that it's a half of MT AC cosine T. So this part right here is simply MT times CT. MT times CT. What is, right? This is MT times CT. So this part is CT. So what is MT times CT? That's our original DSB signal. So the first term here is a DSB signal, our original DSB. But we have one more term here, sine times sine. And right here, we have AM times sine 2 pi FMT. So what is this one? AM times sine 2 pi MT. We haven't defined anything for this because our message is AM times cosine 2 pi MT. But here we say IM times sine 2 pi MT. So we don't know what it is. Okay, we haven't defined anything for this one. So let's just define this part as M hat T. Okay, we'll talk about that in the next slide. So let's call this AM times sine 2 pi MT as M hat T. Okay, just for discussion. Then this part is M hat T. Now M hat T times sine 2 pi FCT, sine carrier. So that's what we have here. So we take this one and using the identity, this cosine alpha plus beta is split it into this way. Now the cosine times cosine becomes our original DSB signal. And the next term, which is AM times sine, we just replace it into M hat T multiplied by sine carrier. And what we want to talk about is this part, mainly. And you see the Hilbert transform here, right? And we're going to talk about that one. Have you learned the Hilbert transform? No. Okay, so this is first time. So let's discuss the Hilbert transform. This is very important in single sideband. Okay, here is a Hilbert transform. Hilbert transform is nothing but a single, just filter. You can say filter. Just some black box. But this is like a filter. Okay, the filter that we know is like a low pass filter or high pass filter, something like this, right? In frequency domain, in low pass filter, typically you pass the low frequency and high frequency component you block, right? So only some part of the frequency you pass it, another frequency region you block it, right? That's typically low pass filter. And high pass filter also. What is high pass filter? Some of the high frequency you pass it, low frequency block. Something like this, right? So that's the typically the filter that we know. So what I'm saying is, let's say low pass filter. When you draw the frequency response or low pass filter, typically looks like this, right? And high pass filter typically looks like this, right? Yeah, see that here's a low pass filter, and down here we have a high pass filter. So that's a filter that we know. Right? Low pass filter, high pass filter. So low pass filter is you pass the low frequency only. Here, low frequency. And high frequency, you block it. Same thing for high pass filter, low pass filter, low frequency, block, high frequency, you pass it. But what I'm drawing here is amplitude only. When you talk about filter, we have two things, right? Amplitude response, this one. And there's one more, phase response. There's a phase response. Always when you design a filter, there's a phase response. But a lot of people ignore the phase response. But here there is a phase response also. Okay? That's what I'm going to discuss in a minute. There's also band pass filter, right? For example, like this. you pass only this frequency band. One more filter type is there's a filter type called all-pass filter. What is this one? What is an all-pass filter? The amplitude, what I'm drawing here is amplitude response, right? Magnitude. Magnitude response is this one. You pass everything. That's an all-pass filter. Why do you need this? In this case, right, why do you need low-pass filter? Because you want to block the high frequency or low frequency, or you want to block the other frequency. But in this case, everything passes. In that case, why do you need this? Whatever comes in, you just pass. Everything just passes. In that case, you don't need this, right? Because everything just comes in, everything passes. So why do you need this? This Hilbert transform is almost like an all-pass filter. Okay? Then why do you need this? Anyone idea why? So what I'm drawing is a frequency domain. Okay, frequency domain. So this is a frequency domain response of a filter. So what I'm drawing is magnitude response of your filter. Okay, typically HF is the frequency response of your filter, right? Frequency domain response. And this is a magnitude. So whatever you comes in, you keep the same magnitude and pass. In this case, your magnitude, let's say you get some frequency component and magnitude becomes 0. So that's same as blocked. But in this case, magnitude, nothing changed, just pass. Then again, the same question, why do you need this? Yes, the reason is magnitude, the magnitude, right, may be same. So you just pass it. However, now this filter will change the phase of your input signal. Now the input signal, output signal, magnitude or amplitude is the same, but now the phase is different. This filter will change the phase. So when you draw the phase response, let's say like this, right? When you draw the phase response, now the phase is changed. Some other things. Okay? It depends on what filter you design, but your phase is now different. That's what we call the all-pass filter. And this Hilbert transform is something like this. Now let's take a look at here. Here's a Hilbert transformer. Let's say this capital HF is the frequency response of this transformer. HT, this is time domain. Okay? So you get an input XF. Again, let's look at the frequency domain because it's easier to look at the frequency domain. Let's say we get some XF, the input signal in frequency domain. And this is the frequency response of this block, like a filter. And we get output. Output is X hat F. Okay, that's the relationship. This is the input. This is the filter frequency response. We get the output X hat F. Okay, that's the relationship. Now this our HF, this filter looks like this. This is our frequency response of this particular filter. And we need to understand what this means. First of all, this means minus j times signum function. This is called the signum function. Signum function f. And what is a signum function? Signum function is very simple. It's like this. Like this. What that means is if the input is positive, right? Input is positive, it doesn't matter the value. Maybe input is like a plus 5, plus 0.1, plus 10, plus 100. It doesn't matter. The output is just 1. If everything positive, output is 1. And if the input is negative, minus 1. So output, the signum function, is output is only 1 or minus 1. Input can be anything, right? You can get any input. But output is only 1 or minus 1. It's like you are taking only sign. Okay? If the positive, then you can make a plus 1 output. If the some comes in, the input is negative value, then the output is going to be minus 1. So that's a signum function. Signum function, right? And this transformer, Hilbert transformer, is this kind of signum function over f times minus j. And what is a minus j? It's a phase rotation. J is a 90-degree phase rotation, right? And since this is minus j, what that means is minus 90-degree phase rotation. That's what this guy does, typically. But now, since we talked about all-pass filter, let's think about the magnitude response of this particular filter. Magnitude response. So let's take a magnitude, or let's take an absolute value. Signum function always get 1 or minus 1, right? So when you take the absolute value, this is going to be 1 anyway, because the output is always 1 or minus 1, right? So absolute value is always 1. J, what is the amplitude? 1. When you take the absolute value of j or minus j, the absolute value or magnitude is 1. So when you take the magnitude of all these things, it's always 1. Okay, so this filter is like this. Magnitude is always 1. It's always 1. Okay, always. In frequency domain, magnitude response is 1. So magnitude is not important. That's what I'm trying to say. When you learned low-pass filter, high-pass filter, band-pass filter, right? When you learn this kind of filter, okay, when you learn this filter, the important thing was magnitude response. This is magnitude response, right? Or amplitude response. That was the important thing at that time. Magnitude response was important. But in this case, magnitude is not important because it's 1 all the time. It doesn't matter, right? What is important is phase response. Okay, phase response is important in this filter. Right? Magnitude is always 1, so forget it. Now we want to look at the phase response. Let's look at the phase response. Let's say our frequency input is positive. Okay? Let's think about positive frequency. If we get the positive frequency, then based on the definition of signum function, this is a positive. It doesn't matter. Maybe frequency is positive 100, positive 1 million, doesn't matter. The output is 1. In that case, HF becomes minus J because this part is 1, right? So F is positive, you get minus J. Now, that's what I said here. Let's say now the frequency is negative, right? Doesn't matter, negative minus 1, minus 100, doesn't matter. If the frequency is negative, now then this signum function has output of minus 1. So minus 1 times minus j, it becomes j. So negative frequency, this particular filter becomes j. Positive frequency, this particular filter becomes minus j. That's it. That's it for Hilbert transform. That's all we have in Hilbert transform. Okay? Minus j in positive frequency, j in negative frequency. Okay? That's it for Hilbert transform. Now go back to this. Remember that the relationship between the input and output and this filter. Let's think about time domain. Let's say xt is an input signal in time domain. ht is a filter response in time domain. And let's say x hat t, let's say is output. Then what is the relationship between these two? How do you get the x hat t? X hat t is a convolution of xt and ht, right? Convolution between these two. Looking at the same thing in the frequency domain. Now x hat f, this is a frequency output. This one equal to hf times xf, right? It's a multiplication, not convolution, right? Time domain convolution, but frequency domain multiplication. Remember? So that's why x hat f is hf. This part is hf, right? Our frequency, our filter response in frequency domain, hf times xf, right? That's the output. But this hf sometimes becomes minus j in positive frequency, or this one becomes j in negative frequency. So that's why, depending on the input is positive or the frequency is negative, now this output x hat f becomes this or this. If the frequency is positive, you get this one. If the output, if the frequency is negative, this is going to be the output. Okay, that's a Hilbert transform, simply. That's all about the Hilbert transform in mathematics. But the problem is that everything, all of these things, equations are in the book. But when you read this book, it's not easy to understand, right? I cannot feel what this means. So that's why we need to understand what this means. Okay, let me tell you what this means in graphical way, just to help you understand. Here's what basically means. Let's say our original input, xf, here's xf, the input, x hat f, that's our output, right? And as it said, as the slide said, our hf is a Hilbert transformer, so therefore the output is either this one or this one, if the f is positive or f is negative. So let's understand what this means. Let's say our xf, our input signal, has this kind of frequency response. Okay? So this is our xf. Here, our input frequency. Input signal transform to a frequency response. Now put this signal into HF here. And see what is this one. What is the output frequency response looks like. Here you see that we have a positive frequency and we have also negative frequency inside this XF. But in this Hilbert transform, now you get different output when you get the positive input or positive frequency or negative frequency, you get different output, right? And difference is that in this case you multiply minus j, or negative frequency you multiply j. And minus j means minus 90 degree phase rotation. J means 90 degree phase rotation. So what you can understand now is that this is the input to the Hilbert transformer. And let's think about this positive frequency. Okay? This positive frequency, what that means is you are having minus 90 degree phase rotation. Okay? And this negative frequency, white one, you have 90 degree phase rotation. So let's do that. Okay? Let's do that. Now, in order to help you understand what that phase rotation means, I'd like to think about three-dimensional, 3D plot. What you are looking at here is a 2D, right? Now think about we have one more axis here. Think about 3D. Here, here, 3D, right? We have like a this. We have x-axis, and we have a y-axis like this, and we have one more axis like that. Okay? Look, think about 3 dimension. This is the original XF, like that. And what I'm trying to think about is phase rotation is on this axis. So phase rotation is like like turning this way. That's the phase rotation. So from here, you are going that way, right? Let's think about there's one more axis here. Then there's a rotation this way. Not this way, but this way. Okay? So 90 degrees is going this way, minus 90 degrees going that way. You know what I'm saying? Think about 3 dimension. I'm talking about that starting here to going that way, like this, right? That's a phase rotation. So 90 degree means you are going that way, minus 90 degree going this way. So when you do that, what that means is my original signal here, the positive component has a minus 90 degree phase rotation. So that this part is now going minus 90 degree phase rotation. So it becomes, this part becomes this. Minus 90 degree. And this negative frequency has the phase rotation of 90 degree. Okay? So this part now going this way, 90 degree. So therefore, this one becomes like this. So eventually that picture looks like this. That's what I'm drawing here. Okay? Original picture looks like this, but after you put this one into the Hilbert transform, the output looks like this. Let me do it this way. So this left one, the positive frequency, that's this hand. This part, right? Negative frequency is like this. Now when I take the right, left and right, the blue one positive frequency, that's this hand, and negative frequency, the white part is this hand. When I take the Hilbert transform, what happens? It's like this. Okay? Phase rotation is going this way. So this positive frequency is taking minus 90 degree, negative frequency going plus 90 degree phase rotation. So it's like this, right? Originally it was here, but positive minus 90 GA, negative frequency going this way plus GA. That's the output of the Hilbert transform. So when you look at this, right, only difference between this original input and this output is that only difference is phase. The shape looks same. When you take the magnitude, then this one has the same magnitude as this one. Okay? Its shape doesn't change. Magnitude, nothing change. Only change is phase rotation like this. That's what happened here. Okay, that's it. That's it for Hilbert transform. So remember some picture like this. Okay, this. Remember those things. Phase rotation. That's the Hilbert transform. It's not that difficult, right? Once you understand this picture, that's not that important. As an example, let's think about this one. You know what cosine looks like in frequency domain, right? This is a cosine in the frequency domain. We have a cosine, and this is the cosine frequency, Fc and minus Fc. So it's like when you put the cosine, it becomes like this, right? Positive, negative frequency. Now let's put this cosine as the input to the Hilbert transform. Let's cosine put it into Hilbert transform. Then what happened? It's like this, right? Like this. So it becomes like this. Positive frequency minus 90 degree, negative frequency plus 90 degree. Like this, right? What is that? That is actually sine. When you draw the sine, everyone know that when you put the cosine, it looks like this. What about sine? Maybe someone say sine looks like this, right? That's some people remember that way, sine. But that's correct. That's actually wrong. Sine is not this one. It's this one. Okay? We have 90 degree phase. Okay, that is more accurate. Cosine has no phase. This one phase is 0. But in sine, actually there is a 90-degree phase rotation. So this is wrong. This is correct. So this is correct. That is a sine. So put this cosine into the Hilbert transform. The output is going to be sine, like this. Okay? So positive going that way, negative frequency going the other way. So remember the input-output. Cosine, put it into Hilbert transform, output is sine. Remember the relationship between cosine and sine, okay? Cosine and sine. So that's why going back here, that's why that's why what we are trying to do is that this is our original MF. Okay, let me put it back a little bit further here. Let's come back here. Let's say our original XF, as I said, is this one. XF looks like this, and put that into the Hilbert transform. Now, the output, this is XF. Output of the Hilbert transform looks like this, right? Looks like this. That's the output. That's what you can see here, right? That's the output of the Hilbert transform. Now, what we want to do is coming back to our upper sideband. Okay, we were discussing the upper sideband before in the previous slide. So this is upper sideband. Now, when you take a look at the first term, this is message times cosine. So when you do that, this one actually is the same as our previous ST in DSB. So this is like a DSB signal, right? Remember the DSB? This is one exactly the same as the DSB part. So DSB looks like this in frequency domain. Okay, this one same as a DSB signal. Okay, mathematically this is a DSB, and frequency domain this is a DSB, same thing. In upper sideband we have one more term, minus half of the A. This is carrier, sine carrier, and times m hat t. And m hat t was the Hilbert transform output of mt. Okay, our mt was here. Put it into the Hilbert transform, then we get the m hat t. So now then, what was our mt? Going back here, our original mt. Let's say this is our original mt. Just the example, right? That's what we are discussing here. Okay, let me see. Our original MF looks like this. Original one, original message. Okay, this is our original message. Okay, in frequency domain. Now what you want to do is original message, you want to put the cosine into here. So this is a DSB signal, right? So in frequency domain, this one now is changed into this, right? So this is a DSB-SC signal, this one. What you want to do also is you want to put this one into the Hilbert transform. This is our original message, right? In frequency domain. Put this one into the Hilbert transform. Then what was the output? Then as we said, this is the output, right? Using this output, now what you want to do is, that's the output. What you want to do is, let's say, let's multiply sine here. You want to multiply sine. From here to here, you are multiplying cosine. And then you get this. Now you get this signal, Hilbert transform output, and this is m hat t, for example. This is a frequency domain, but in time domain it's m hat t. In here, now you're multiplying sine. That's what you want to do here. When you multiply sine, now what happened? This is the original m hat t, and now you multiply sine. Then what happened? Original sine looks like this, right? Okay, remember, not this one, right? Like this. That's a sine. Now you want to multiply this one with this. So this is our original m hat t, but this is frequency domain. Again, this is sine, but frequency domain. So both are frequency domain. So let's multiply these two. When you multiply these two, now what happens is this one, which is in here minus j, this sine is also minus j, right? Minus j times minus j, it's like a minus 90 degree. This one also minus 90 degree. So when you multiply these two, what happens? It becomes like this. Minus 180 degree, right? Because you are adding these two. Multiplying these two, it's like a phase addition. 90 degree, minus 90 degree, minus 90 degree, you are adding together minus 180 degree. Looking at the negative frequency, here you have 90 degree, okay, 90 degree, and we have also 90 degree in sine. When you multiply these two, it's going to be 180 degree, right? It's like 180 degree. So that becomes 180 degree, right? Is it 180 degree? No, actually, I'm sorry. No, that's not the case. Okay. No. Okay, let me take it back. Okay, here's what happened. Yeah, right. Okay, think about this way. In here, in time domain, we are multiplying two different signals in time domain. Okay, multiplying this one with this in time domain. And we are looking at the frequency domain of sine and frequency domain of m hat t. Multiplication of two different signals in time, it's going to be convolution in frequency, right? It's not multiplication, these two, because in time domain, it's multiplication. In frequency domain, it's a convolution, right? So let's do convolution of these two. Then what happened in the convolution? When you put this one, flip and slide to do convolution, okay? Then what happened is, right here, you have a minus 90 degree. So when this slide, this whole thing becomes minus 90 degree onto here. So therefore, this whole thing now is like this. But when it slide, you are adding minus 90 degree by this one. So it's like this one. It's keep going, like it keeps sliding. And this one is like positive 90 degree. So you are adding positive 90, like this. Yeah, so it becomes like this. Okay? So this is convolution between these two. Convolution. So therefore, when you do the convolution of these two in frequency domain, now you're going to get this output from this part. Okay? Think about it. Okay? So therefore, eventually, this one minus this. So this one minus this means I just want to multiply minus here and add it, right? I can do that, right? Because this one minus this, when you do that, you're going to get this output. Okay? You're going to get this output. When this one minus this, you're going to get this. So that's how you get the upper sideband. So simply speaking, in order to make a single sideband, in upper single sideband, what you need to do, is first you make a DSB like we did before, and then put this original message into the Hilbert transform. Now you get this and multiply the sign, and then you are doing subtraction. Then you are in the upper sideband. Similar thing can be done in the lower sideband. Only difference is in this lower sideband you are doing addition. In the previous upper sideband you minus, right? In the lower sideband you are doing addition. Then you are adding this together. Now you are inner ones. Okay? That's the upper sideband, lower sideband. Okay? Okay, so let's discuss in the next time.